I'm Alec Harley, Director of ScotlandIS in Scotland, and it's my great honour to introduce the Young Software Engineer Awards that we've been sponsoring for over 30 years. But first, a quick word from one of our graduates, Liam Davis.
Hi, I'm Liam, a technical graduate here at ScotlandIS. I'm at the beginning of my own journey in the tech industry, just like many of you here today, and it's incredibly exciting to see the talent and innovation in this room. We're really pleased to be sponsoring these awards because we know that our future will be designed and delivered by people like us, those who are passionate about technology and determined to make an impact. Whether it's working on cutting-edge projects like using data to improve public services, or exploring the potential of quantum computing, or developing digital twins, we can transform industries. The technology we're using today is shaping the skills we'll all need for tomorrow. At ScotlandIS, we've been a part of Scotland's technology landscape for decades, supporting critical initiatives like keeping the wheels of democracy turning at the Scottish Parliament, or ensuring the safety of our skies with NATS.
But what's truly special about today is the recognition of your achievements. The nominees, your peers, and even those who might not know what they want to be in the tech industry at the moment. It's your ideas, creativity, and the passion that will drive the industry forward.
So from one tech enthusiast at the start of his career to another, I wish you all the best of luck. You're the ones who will shape the future, and I can't wait to see what you achieve. Now, let me introduce the class of 2024.
My name's David Topping. I studied at the University of Dundee. I did computing science, and my honours project was the University of Dundee Library Occupancy Tracker, which I decided to call LiBusy. The aim of it is to sort of give students an overview as to how busy the library is going to be based on past data. So not only does it show how busy the library is overall, but it shows the busyness section by section, and this is live data as well, to allow students to better plan their visits to the library. I know a lot of other unis have sort of similar systems, but none of them showed a section by section breakdown of how busy each section was. And often when I'd go to the library, I would choose times that were really busy, and I would always want to know beforehand how busy is the library actually going to be. And what does everyone really have on them most of the time is at least one Wi-Fi device. I came up with this idea of scanning the area to see how many devices were in that area, and then by putting a sort of sensor with a Wi-Fi antenna with a known range, we could say for this section there's this many devices, and then overall we know the max occupancy by device would be, so we can sort of say live how busy the sections are. One of the main considerations we had to take into was the privacy of people. It was a big factor because the library don't want sort of Wi-Fi packages from their users being stored. None of the Wi-Fi packages were stored, it's just counting the MAC addresses. There's a few things that I would want to sort of change if I did put it into production. Try and have more than one sensor per each section. The biggest problem you'd find with this project is just people unplugging the sensor and then having some form of redundancy for connecting to the Wi-Fi as well. I've been doing a bit of investigation into starting a bit of a business. Is it busy anywhere? Because you could put these sensors, cafes, nightclubs, late night venues, bars, anywhere. It was really fulfilling to see all these things come together to come to a practical application that people could actually use. If you look at the app, it looks so simple. It's just a few graphs showing you how busy each section is. But to know what's going on behind the scene is quite rewarding. That a lot of work went into doing that.
Ben Laurie's project, exploring the use of hyperbolic neural networks within class incremental learning, received top marks from the University of Aberdeen, with the markers commending his outstanding technical knowledge and software engineering professionalism. Despite the rapid acceleration in hyperbolic learning literature over the past decade, there remain areas which are yet to be fully explored. This project investigates a clear gap in the literature, explaining strategies and experimental setups that highlight hyperbolic continual learning as a viable alternative to the de facto Euclidean learning widely used in computer vision applications. The Young Software Engineer of the Year judges felt that Ben's project was a great example of undergrad research into a very fast-moving commercial area, and that he did an excellent job of laying out the problem and research in a well-structured and detailed way. They felt the project demonstrated an excellent understanding of existing research in a scientific area and presented a refreshingly clear explanation of a highly complex topic.
I'm Ben McDonald. I studied computer science at Strathclyde University, and my project was titled Escaping Identity Providers protecting privacy with verifiable credentials integration in the community solid server. A few years ago, the inventor of the World Wide Web, Sir Tim Berners-Lee, he realised that one of the biggest issues with it is that users have very little control over their data. Large companies are able to store and process the data of millions of users. Users often don't really know enough about how their data has been used, when it's been collected, in order to really consent to it. One of the solutions to this proposed by Sir Tim Berners-Lee is the SOLID project. So this is a web decentralization project which aims to give users their own personal online data stores. So basically my project looked at the authentication protocol that's used in this. There was an issue with the OpenID Connect protocol that SOLID uses, and that verifiable credentials could be a solution to this. Well, basically in this system, the holder would be a user and an application. The user would need to fully trust the application to hold their verifiable credentials and use it. Whereas in Solid, usually users don't have direct control over the application. In my revised version of this protocol, I split the holder into two separate entities, the app and the user, to make it a bit more secure in that context. It's not really a very mainstream subject, it's kind of hard to find resources. A lot of it was just in academic papers and web specifications. When it came to integrating it into the community solid server, it's a very big open source project. So I had to spend quite a lot of time looking at the architecture and figuring out how I could make modifications that would be able to integrate this new protocol while also respecting the design principles that it's built on. When I was doing my dissertation, I had a paper published and it's called the Solid Symposium 2024. So it's like a workshop that was hosted in Belgium in May. I was attended by industrial experts, academic experts who are working on Solid, and they seemed to have some interest in implementing this and incorporating this protocol in Solid. It seems like it might hopefully have an impact of some sort.
I'm Benjamin Sonnet. I studied computer science at the University of St Andrews, and my project is wave function collapse as a constraint solver for game level generation. I had an interest in video games and procedural content generation, so I thought it would be cool to be able to create my own game from the knowledge around wave function collapse. In the context of video games, it is very frequently used as a level generator. Maybe it has like a water tile, a dirt path tile, a stone path tile, and it will put those together to create a finished level. By defining like how you can put them together, it will use those rules to create like a map with these tiles. I made like a game demo that uses wave function collapse, but also extends upon it with things like infinite modifying in blocks. In a lot of wave function collapse algorithms online, it's just on a like finite grid, like linking it together with the idea for backrooms that you're in an infinite expanse. Having like a small level doesn't really work. So this infinite modifying in blocks technique, it kind of breaks the generation into layers. So you apply wave function collapse to an infinite level while still having each chunk look the same. The biggest challenge was trying to balance all the different components that I had to work on. I ended up having to code my own wave function collapse algorithm from scratch. My project ended up being more like a demo in a way, where the game serves more to demonstrate the concepts that I then discuss in the report and serve as like an overview of wave function collapse and all the different things people have tried when implementing it, and like all the issues they might have faced and how they've addressed them. It was a fun project to work on, especially with being able to have it more in the context of like a video game. You write the code, but then you could actually like press generate and see the level like pop up in front of you, and that's like a really cool thing.